When the first edition of Newton's Philosophiae Naturalis Principia Mathematicus was published in 1687, fewer than 400 copies were printed by a Royal Society strapped for cash and relying on Edmund Halley to assume the financial risk. As 40 copies were given to Newton to distribute to his colleagues in Cambridge, and some other number were provided to various dignitaries, including King James II, copies were hard to come by, especially outside of England and Holland. This scarcity is illustrated by a story told about the Marquis de l'Hôpital, whose name is probably familiar to those listeners who have had occasion to take a first-year calculus course on account of his rule. L'Hôpital was struggling with a problem in hydrodynamics having to do with the determination of what sort of shape would generate the least amount of resistance, or drag as it is called, as the object moved through a fluid. When he spoke of his struggle with the Scottish mathematician John Arbuthnot, Arbuthnot told him that the answer to his question was to be found among the many other results of the Principia. Another person in the room where the conversation took place recorded L'Hôpital's response to learning this information. Quote, "He cried out with admiration, 'Good God, what fund of knowledge is there in that book?' He then asked the doctor every particular about Sir Isaac, even to the color of his hair. 'Does he eat and sleep? Is he like other men?'" End quote. Truth be told, as we have examined in some detail, Newton was not like other men, and his book was not like other books. Instead of philosophical ideologies and references to ancient thinkers, it established its conjectures on experimental evidence and mathematical demonstration. It offered a comprehensive synthesis of the means of motion of all things in the universe, but it relied on occult and strange forces to do so. It was breathtakingly brilliant and maddeningly inaccessible, much like its author. 25 years later, with his ideas still being questioned in many places in Europe, Newton published the second edition of the work, this time with greater numbers and to a better reception. With this, and a growing number of converts in Europe, the tide began to turn. When the third and final edition of the book was printed in 1726, the movement to establish Newtonian mechanics was well underway. Still, though, it would be another 50 years before it was completely accepted, along with the final triumph of the heliocentric system. Today, only about 150 copies of that first edition still remain. They are carefully guarded and maintained in climate-controlled vaults in various places around the world. At Cambridge, there is even a copy in which Newton himself made his notes as he worked towards that heavily revised second edition. So esteemed is the book that when a copy was put up for auction in 2016, it was sold for a sum of £3 million, or about $3.7 million, by Christie's auction house. The book was one of 80 copies explicitly produced for production and distribution outside of Britain and is known as a continental copy. In this episode of the Odyssey, we'll look at the process by which Newton's work came to be accepted across Europe, and with it, the fully heliocentric model of the solar system. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place, Episode 28, The Triumph of Mechanics. When you listen to the various narratives surrounding the publication of the Principia, there's sort of a fait accompli thing going on. There's this sense of build-up from Copernicus through either Galileo or Descartes, with all sorts of tension and conflict, and then Newton steps onto the stage, gives a sort of Shakespearean monologue that jumps the plot forward to a new place, and all of the difficulties are resolved. If only the history were quite that tidy. While Newton's work did make a bold and definitive statement, it really needs to be understood what that statement was, why it was important, and how it came to be accepted in spite of that one glaring problem that we've talked about. So let's take those things one at a time. First, what was the Principia and what made it so different? As we mentioned in our episodes on the scientific revolution, the Principia was a culmination of a move away from what was called natural philosophy to something known as either mathematical or experimental philosophy, though I should be clear to say that what we call experimental philosophy back in the late 16 and early 1700s is very different than what we call experimental philosophy today. Prior to Galileo, there was an emphasis on needing to understand the causes for things. If you didn't know the causes, in their complete, fourfold Aristotelian fullness, it was thought that you really weren't doing philosophy. While observation of the natural world might intrude on this from time to time, the natural philosophers believed that it was primarily through the use of reason that one arrived at an understanding of the physical universe. This all begins to change with the work of Galileo and the writing of Francis Bacon. Galileo emphasizes, along with Kepler, the centrality of describing nature using mathematically expressed natural laws, while Bacon focused on the process of experimental examination of phenomenon as the basis for knowledge. Newton's two great works, the Principia and Optics, realize these two shifts in their fullest and most dramatic ways. The Principia, with its three laws of motion and its universal law of gravitation, applied through rigorous mathematical demonstration to a vast array of problems, refutes that a rational consideration of cause is the most effective approach to understand nature. Instead, causes are specifically set aside and replaced with detailed mathematically expressed physical axioms that are then developed comprehensively. As we will discuss, Newton feigns no hypotheses, at least in the first edition, as to why the universe obeys certain natural laws. He only demonstrates that if such laws are taken as given, i.e. that force produces acceleration or changing velocity that is proportional to the force and inversely proportional to this thing called mass, then the application of those laws to real-world systems, albeit fairly simple ones, at least initially, predicts the behavior of those systems with reasonable accuracy. Causes, therefore, are replaced by mathematical laws. In optics, working with the methods first put forth in Boyle's Skeptical Chemist based on Bacon's writings, Newton develops descriptions of natural phenomena on the basis of careful experimental work, observations of highly controlled physical systems where the system's physical quantities are varied with great precision, and then the behavior of the system is documented to arrive at clear relationships between the properties of the system being investigated, in this case, light and its interaction with matter. Here again, in this experimental philosophy, the development of facts based on those observations supersedes the opinions of philosophy or ideology. While we usually take these things for granted today, it is absolutely true that in 1550, almost no one would have accepted them. It is for this reason that I believe that we can say in the 150 or so years following Tycho's decision to collect better data to better evaluate the competing cosmological models of his day, a true revolution in thinking occurred, whose reverberations are still being felt and debated over even this day. Newton's two great books mark the completion of the scientific revolution and the triumph of empirically based knowledge over that arrived at through ideological means as a way of understanding the natural world. This, I believe, also addresses the question of why Newton's work was so important beyond the obvious sense that it more accurately described the phenomena of the physical world it addressed, notably mechanics, both celestial and terrestrial, and light and optics. This leads us then to our third question. How did Newton's work come to be accepted? and this forms the bulk of the first part of our episode here. So let's look at the situation in Britain to begin with. One of the things that's rather interesting is that for a variety of reasons, British mathematicians and astronomers seem to have been much more favorable towards Kepler and his ideas than almost any of the other intellectual communities of Europe. Factors contributing to this likely included a predisposition towards empiricism that went back to the days of Roger Bacon and the Oxford calculators, an identification with the Protestant roots of the Keplerian tradition, especially after the Galileo affair and the aforementioned writings of Francis Bacon during the Elizabethan period. As such, the idea of Kepler's diminishing force emanating from the sun found fertile soil to grow and develop in England. While these ideas would be changed significantly just prior to and during Newton's life by men such as Robert Hooke, there was already a predisposition towards the Keplerian picture and a much greater acceptance of his cosmological model. Thus, when Newton puts all the pieces together, the reaction is more of, wow, so that's how it's done. And look at how all this other stuff comes with it, instead of, wait, what? Why are we still working with heliocentrism here? Isn't that just absurd? As we've sort of mentioned many times, the biggest impediment in England was not the conclusions that Newton arrived at, but the overly technical way in which he presented the material. The next problem one would have encountered after those dense mathematics were either worked through, this being the minority case, or sort of ignored, this being the more majority case, was the nature of the gravitational force itself. For many, the idea of stepping backwards from Descartes' mechanical hypothesis of motion based off of the collisions and interactions of vortices to this occult action at a distance thing called gravitation was really a huge stumbling block. Had it not been for the fact that Newton was able to, in the third book of the Principia, completely derive all of Kepler's results and a whole bunch of other stuff, something, as we have said, Newton nearly declined to publish on account of his ongoing dispute with Hooke, there's a pretty good chance that the whole idea might have been ignored. Instead, for those who accepted the ideas of Kepler in celestial motions and Galileo in terrestrial motion, the ability of Newton to bring all of those things under one overarching framework was more than enough to guarantee serious consideration and a grudging acceptance that Newton was onto something. This, of course, was the position of Huygens, at least after the intercessory work of Fatio. The Dutch astronomer and natural philosopher would never be completely comfortable with the idea of gravity as presented in the Principia, but he had to acknowledge its unparalleled success in describing the motions of heavenly objects. It should be noted, however, that there were those in Britain for whom this new cultural emphasis on different ways of knowing things was rather threatening. As London had arisen, phoenix-like, from the ashes of the Great Fire, so its scientific community had gained a new prominence. In the new coffee houses that served as the gathering places of those associated first with the reign of Charles II, and then, later, with the rule of William III and Mary II, the men of the Royal Society gathered with other influential thinkers and politicians to discuss the affairs and ideas of the day from within the paradigm of the newly emergent experimental philosophy and rationalism that was taking hold. Among the names one finds in these circles are Hooke, Wren, Halley, Locke, Huygens, Flamsteed, and, in time, Newton, among many others. From this group came a number of profoundly influential books deeply ensconced in what would become known as British empiricism, from Locke's two works on political theory published during this time. Other examples include Boyle's Skeptical Chemist, Hooke's Micrographia, and of course, Newton's Principia. On the other side of this, though, was a group of what might be called literati, who saw the new way of thinking as a step in the wrong direction. Chief among these were the classicist Sir William Temple, his on and off secretary Jonathan Swift, and eventually Alexander Pope. In 1680, just a few years before the publication of the Principia, Temple published a somewhat scathing essay extolling the virtues of the ancient classics over the modern works of art and experimental philosophy. In language strongly reminiscent of the modern debates on similar kinds of topics, he wrote that printing had merely increased the number of copies of books rather than the number of good books. He said it was the earliest philosophers, men like Plato and Aristotle, who were the best, and writings by men like Descartes and Hobbes would soon be relegated to the trash bin of history as being of little importance. As is usually the case with these sorts of "get off my lawn, you kids" sort of proclamations, said history has not been really kind to Sir William, who is now known as little more than a historical footnote, while men like Descartes and Hobbes are standard fare in university educations. Jonathan Swift, on the other hand, has fared a good bit better, as his use of satire has ensured the longevity of his thoughts. Even though most people today are unaware that works such as Gulliver's Travels were articles of biting sarcasm directed at things like Hooke's Micrographia, the fantasticness of his descriptions are still treasured, though one gets the sense that all seems a bit more like science fiction now than social commentary. Pope would enter the fray at the age of 23 with his work, An Essay on Criticism, which offered forth the ageless line that a little learning is a dangerous thing. Here again, however, there's not just a bit of irony in that it is Pope's epitaph of Newton, whose work Pope, by the way, just despised, that is among that man's best remembered. Quote, "Nature and nature's law lay hidden night. God said, let Newton be, and all was light." End quote. Concurrent with this battle of the books, as Julie Wakefield calls it, there was a rising conflict between science and religion. There were those, Leibniz among them, who saw in Newton's work the removal of a creator actively involved in the working of his creation. While this is not how Newton saw his work, even in the slightest, men like Halley did take the step of moving to a view that God mostly worked in the cosmos through the use of universally established natural laws. While such an idea is much more commonplace among those scientists who hold theist views today, this position was a good bit more scandalous in a time when it was held that the Creator was intimately involved in every detail in the creation. To get a sense of the somewhat seismic shift that was taking place, allow me to relate to you an exercise I do in my class on the history of philosophy of science. When I ask my students to answer the question, "Why do objects fall?" during a class discussion, every one of them gives me the same answer. Can you guess what it is? They all say, "Well, because of gravity." Now, if I then ask them what gravity is, their response is either, "I don't know," or "It's that thing that makes objects fall." And of course, what makes objects fall? Gravity. And what's gravity? Well, it's what makes objects fall. And you kind of get a sense that they really don't know what's going on here, right? And here, one should forgive them for the vagueness of their answers. I think it's, pretty understandable, as they're not really all that far from Newton himself in their lack of a definitive answer as to the nature of gravitation. Remember, Newton said, "I offer no hypotheses." What I do next is I show them the words of Jesus from Matthew's account of the gospel narrative, wherein the Nazarene carpenter and itinerant rabbi points out that not one thing falls to the earth apart from the will of the Father. Now, I teach in the American South, and I teach in a region that, like so many others down here in the American South, likes to call itself the buckle of the Bible Belt, thus sort of indicating that, it is among the most faithful regions to the Christian tradition. And so it's probably good to assume, and I'm pretty comfortable saying this, that the large majority of my students have grown up in a culture saturated by that Christian tradition. When I show them the verse, very few of them indicate that they're unaware, of its existence. And yet, as I've mentioned, not a single one of them referenced that verse as the cause of an object's falling. Prior to Newton's work, that would not have been the case in the deeply pious England or its American colonies, especially among those confessing a more Calvinistic faith. To add to this, once I point out this sort of interesting thing, there are always a few students who will then claim that gravity, as a natural law, is really just an expression of God's will, a position very close to that held by Halley and men like him. And it should be noted here that in 1691, Halley was denied a deserved and prestigious professorship at Oxford, in part for holding to those very types of explanations. Today, though, such a position is thought to be rational and reasonable, if maybe a bit post hoc, as an explanation for those who believe that the divine has a place in the natural order. In England in general, and London in specific, the years between 1680 and 1740 are a period when the conflicts surrounding this shift in paradigms from a very theistic to more of a natural law-based paradigm takes place. While both of these battles would be carried on through the publications of London's many printing presses and discussed in those beloved coffee houses and bookstores, it would be a series of events in Europe that would take Newton's triumph in mechanics and establish it as the supreme work of the coming Enlightenment. As we've said, Newton's work was accepted in England much earlier than in other places. Criticism, satire, and occasional mockery aside, England was more ready for a book of the sort Newton wrote than probably anywhere else in Europe. When the heavily edited second edition was published in 1712, it was a much more accessible document. While the mathematics was still difficult, the intervening 25 years had allowed many to upgrade their skill set, and Newton had also toned things down just a bit. Additionally, there was a clearer understanding of which portions of the monumental work could be sort of skipped over as being of a more technical nature and unnecessary for understanding the physical results derived in books 2 and 3. As an example of this, in my first-year physics classes, we do not delve into the fullness of Newton's mathematics to do any of the work. Instead, we're able to apply the 3 laws of motion to an impressive array of different physical situations, from pulleys and masses, to the flow of blood through an artery or vein, to the motion of a planet around the sun, without having to access the tremendously Byzantine geometry calculus hybrid that Newton used. Additionally, after the second edition, there began to appear a few what you might call everyman's guides to the work. Again, these distill out the important results of the work and express them in ways that are understandable to the typical educated reader in such a way that those with a reasonable level of education, whether that be something formal in a university or through a trade or guild, can see how the ideas can be used in the real world. Already willing to accept the obvious assumption of heliocentrism found in the third book, it didn't take much for those in both intellectual circles as well as ecclesial circles to come around to the power and utility of Newton's ideas. Outside of England, though, things were a good bit less smooth. In France, Newton's contradiction of Descartes' mechanical philosophy was not going to go unchallenged. In the various Germanic states, Leibniz's opposition and ongoing priority conflict would present a significant barrier to acceptance. While in Italy, at least for a while, the strong community of classically inclined natural philosophers, the same group that had opposed Galileo a century earlier, along with the opposition of the Catholic Church to heliocentric explanations, would slow adoption there. In the Germanic states, it would be the acceptance of the framework by Huygens and then the ascension of the ruling family of Hanover to the British throne that would help smooth the way for the natural philosophers to come to grips with Newton's ideas. While Leibniz did propose an alternative version of mechanics, the details of which are beyond the scope of this discussion, the superiority of the definition of momentum in the Principia, along with a later understanding that Leibniz's mechanics incorrectly worked with a precursor to what we now define as energy, eventually sank the idea, though Leibniz's slow descent from being the center of court life to relative obscurity also aided the process. In France, the opposition was much more fierce. The proponents of Newtonism centered around a writer, political philosopher, and historian by the name of François-Marie Arouet, otherwise known by his pseudonym, Voltaire. Voltaire, it turns out, was convinced fairly early on that Newton's ideas on mechanics were, in fact, far superior to those of Descartes, especially once he spent some time in exile in England among the intellectual circles surrounding the then very elderly President of the Royal Society. When Newton died in 1727, Voltaire, a product of the Ancien regime in France, was shocked and amazed that a commoner, no matter what cultural accolades he might have achieved, would be afforded the honors and burial usually reserved for only the highest nobility. When he returned to France, he would take that experience with him. He would also become an evangelist for Newtonianism and soon gathered around him a talented group of intellectuals to advance that cause. Among them, and please here, excuse my really terrible French pronunciation, was the mathematician Alexis Claude Clairaut, the polymath Pierre-Louis Moreau de Maupertuis, and a remarkable woman by the name of Gabrielle Mealey De Chetley, Marquis de Chetley. Let's take a moment to talk about the contributions of each. Voltaire would be responsible for writing what became the most influential epitome of the Principia, a book that summed up and extended the ideas of the early work in a way that allowed it to be taught to just any old common person. He also reproduced and extended Newton's experimental work in optics. Of lesser scientific note, but probably more important from a cultural standpoint, he wrote the wildly satirical work Candide, which lampooned the exuberant foppishness of Leibniz as well as his philosophical ideas, thus deflating the sense of intellectual superiority that was sometimes associated with the German polymath. Clairaut would be influential in his reworking of Halley's paper on the comet of 1682 and the date of its return. He would make a more precise set of mathematical calculations based on Newtonian principles that would more firmly establish the viability of Halley's claim, as well as more firmly staking out a date. We'll return to the importance of this a bit later in the episode. Maupertuis is very, very important because he would lead an expedition to Lapland that would provide crucial evidence in resolving the debate between the Newtonians and the Cartesians. This expedition was part of an effort to more precisely measure the curvature of the Earth. The Cartesian position on all of this was that due to the mechanical action of the various vortices in which the Earth moved, the spherical Earth would be squeezed slightly at the equator, thus causing an elongation of the Earth along the poles. Sort of think of like a squishy ball. You squeeze it around the middle, the top and the bottom kind of get pushed up and down. Newton, on the other hand, had argued that the Earth's rotation would slightly counteract the inward force of the self-gravity of the Earth, and thus the Earth would stretch slightly at the equator and be flattened at the poles. Maupertuis' mission was to measure the deviation of a meridian line from a truly spherical arc to determine which of these things was true. His conclusion, gathered from his data, was that the Earth was squashed at the poles sometime around 1736, and it would provide a powerful piece of evidence in Newton's favor. From this, he would then go on to use Newton's ideas to establish what is now known as the principle of least action, something we discussed at some length in our biographical series on Richard Feynman. The final figure in this quartet of French Newtonians is Mealey De Chetley. She was a mathematician and a physicist who had trained under both Maupertuis and Johann Bernoulli, and she did work on the science of fire, which led to the prediction of infrared radiation. She also worked on the idea of conservation of energy, a foundational cornerstone in physics, and argued against Locke's idea of what was now sometimes thought of as thinking matter. During this time, she would publish a textbook on physics, originally written for her 13-year-old son, that was so influential that it gained her election to the prestigious Academy of Sciences of the University of Bologna. Her greatest legacy, however, was a completely French translation of the entirety of the Principia. Published a year after her death due to complications of childbirth, the work would become the standard translation, not only due to its clarity, but also on account of her insightful commentary that extended the Newtonian framework to include the idea of kinetic energy. It's a work that has remained the standard translation of the Principia in French up until the present day. She also wrote treatises on an early form of financial derivatives, the nature of happiness, and the value of women's education. All in all, it's a pretty amazing amount of output from a woman who had to overcome tremendous systemic barriers and only lived to the age of 42. In Italy, it was another remarkable woman who brought Newton's work to her colleagues. In this case, it was the daughter of a Bologna lawyer by the name of Giuseppe Bassi. Laura Maria Caterina Bassi, like Chatelet, had been educated outside the formal system reserved for men when she impressed the family physician by the recording of his instructions for the care of her mother in flawless Italian and French at the tender age of 12. The physician, one Gaetano Tacconi, was also a professor of medicine at the university, and so for the next 9 years after recognizing her incredible talent, he oversaw her education in private. In 1732, Bassi then underwent a private disputation defense, think of that as sort of a modern dissertation defense, in her home in front of a number of the university's faculty, and as a result was elected a member of the Academy of Sciences as the result of the brilliance of her ideas. A month later, she then performed a public defense of some 45 theses, and based on that, the acclaim acquired from that, was awarded a doctorate from the University of Bologna. Only the second, by the way, awarded to a woman anywhere in Europe. Following a third disputation defense about a month later, again in public, the city of Bologna appointed her a professor at the university, the first such appointment of a female to a full academic post in the history of Europe. While all of this did sort of have the air of a publicity stunt, there is no denying that Bassi was deserving of all of the honors she achieved. And while she would continue to fight institutionalized sexism and gender bias throughout her life, she and her eventual husband would carve out a place for her and for both of them in the academic world. The subject of Bassi's disputations were the mechanical hypotheses of Descartes and Newton, and in each case, she refuted Descartes through the use of Newton. However, due to restrictions placed on her teaching at Bologna, she was only allowed to sort of do one disputation defense a year and never to have students, because I guess it was thought to be untoward to have a woman teaching men at the time. Bassi and her husband, a little-known physician by the name of Giovanni Giuseppe Verratti, began offering classes in their home. Eventually, they would add a laboratory to the space in order to conduct experiments, often in the emerging field of electrical work. Of course, most prominent among these topics discussed were Newtonian mechanics and the newly emergent Franklinian electrical theory. One of the students who attended these sessions was the young Alessandro Volta, who would go on to invent the first electric battery. Belli would be recognized in a number of other ways, and it was her correspondence with a large number of intellectual figures across Europe that did much to spread Newtonianism as well as restore the flagging reputation of Bologna and its Academy of Sciences as a serious and significant set of academic institutions. And it was through figures such as these that Newton's mechanics spread throughout the intellectual community of Europe and displaced both the ideas of Descartes and Leibniz. What is interesting, though, is that in no way does Newton's work meet with the institutional pushback or intellectual scorn other heliocentric models did. And so a fair question can be asked. In light of the continuing lack of direct observational evidence, why was that the case? So now we come to what I think of as the central theme in today's episode, and in some ways, the central theme of this entire series. By the time you get to about 1742, the year of Halley's death, Newton's ideas in mechanical theory are becoming ascendant in the areas of experimental and mathematical natural philosophy. Along with this, there is a growing acceptance of a heliocentric model of the solar system that is essentially the Keplerian model as explained by Newtonian gravitation rather than Kepler's swirling or circulating magnetism-like force. The interesting thing, though, is that there really hasn't been a whole lot of new observational evidence acquired to support this sort of general broad acceptance of heliocentrism. There hasn't been any sort of killer fact or killer observation, to use David Wooten's term, that puts lie to the geocentric models, which are, by the way, at this point, modifications of the Tychonic system to account for the elliptical orbits proposed by Kepler. So why does this shift take place in the absence of something like that? Where is this killer fact, as it were? This question has bedeviled both historians and philosophers of science since the discussion of something like a scientific revolution began, with many of the attempts to understand it leading to the downfall of otherwise promising ideas about what makes science science. Probably the best answer that I've come across has to do with something known as the problem-solving approach to establishing what is known as a demarcation criteria as to what makes something scientific. In this view, when an explanation of nature is better able to explain the various existing observations and also account for either previously unexplained phenomena or make entirely new predictions that turn out to be correct, the new hypothesis is likely to supersede any previous ones, even if it is vastly different in character than what was held before. Newton's synthesis of celestial and terrestrial mechanics, along with the proposal of the action at a distance gravitational force, is a clear break from the ideas of those before him, whether they be Aristotelian or Cartesian. Nevertheless, so successful is his synthesis that it becomes just impossible to discount his overall structure. Whether it be his handling of the continuous nature of motion using the ideas of mathematically representing change through the tenets of calculus, his identification of momentum and its change due to force, and thus understanding acceleration in ways that no one before him really had, or his ability to offer a clear path to treat any number of previously unsolvable problems through his laws of motion. Newton's framework went so far beyond anything before him that, like L'Hopital, those who encountered the broad scope of the work were astonished by it. This comprehensiveness extended to the models of the planets and the heavens using the exact same sets of rules. Additionally, heliocentrism was fundamentally built into the Newtonian model. Newton couldn't have done what he did without assuming the solar system was heliocentric. As such, if one were to accept the validity of Newton's terrestrial physics, there was a strong inclination or push to have to accept his celestial physics as well. While I suppose it would have been possible to create a geocentric model based in some way on similar physical principles to those Newton put forth, it would have all seemed rather ad hoc or post hoc, and while there were those who might have advocated such an approach, they were now fighting quite the uphill battle. The other development in thought in the late 17th and early 18th century was the rise of what might be called hypothetical thinking. While certainly not exclusive to this time, the ideas of hypothesis formation, testing, and modification really come into their own through the work of men like Boyle and Halley. When you read the various things published by Kepler or Galileo, you can see they're still trying to work to provide mathematical demonstration of their conclusions in order to establish the veracity of their work, their conclusions. In other words, they're still trying to prove everything they're saying, though in these cases their proof lies in deductive mathematical work that rests on empirical evidence rather than in some sort of chain of reasoning from earlier philosophers. Neither man seems to be comfortable with the process of creating a hypothetical explanation of a phenomenon and then working out tests of the hypothesis to show that it is either the most likely or best explanation of the observations. By the time of Newton, this is much more acceptable, especially in England. Boyle's work with air pumps has made hypothetical thinking much more the norm, and while men such as Flamsteed will struggle with this, others like Halley will show themselves very comfortable with accepting a hypothesis on the basis of its strength to best explain the observed natural phenomenon. In this, Newton's mechanics is so far ahead of its competitors that to hold a variant idea requires either a strong commitment to an ideological position in the face of enormous physical evidence to the contrary, or just something like blind faith. Now, this is not to say that had there been observational evidence found that contradicted Newton's synthesis, it wouldn't have relegated Newtonian mechanics to the trash bin. But as Newton's ideas became known, there were a number of tests that were conceived to evaluate it. Probably the earliest, one of the easiest to understand, was that thing about measuring the shape of the Earth. If the Earth was either a perfect sphere or stretched at the poles, that would have flown directly in the face of Newton's predictions at both the cause and the effect levels. When the Lapland expedition of Maupertuis found that the length of a degree of a meridian arc was distorted in just the way Newton predicted, this was a piece of very strong confirmational evidence that the Earth did in fact rotate. While it was possible to make the claim that God had just sort of created the Earth in this sort of non-spherical shape that was flattened at the poles, such an argument was profoundly post hoc, or after the fact, and was thought to be significantly inferior as an explanation compared to the full picture Newton had presented that used the second law of motion and the universal law of gravitation to explain the shape of the Earth, and then used that shape and the effect of the moon's gravitational influence on the equatorial bulge to account for precession. Using inference from best explanation, Newton's ideas gave the best account for the interrelated physical phenomena that had been observed. It should be understood, however, that Maupertuis' measurements and subsequent conclusions were not the only supporting evidence now coming in to support a heliocentric model, either that of the Newtonian or some other version. As I mentioned in the episodes on Galileo, in around 1612, the Tuscan natural philosopher had arrived at a mathematical expression for predicting the times of the eclipses of the moons of Jupiter, i.e., when the 4 large moons would pass behind the giant planet. In this prediction, Galileo had to include a correction term that he correctly interpreted as being due to having to correct for the motion of the Earth around the Sun. As others looked at his work and the measurements being made, they found that his expressions worked well in some cases, but less so in others. In 1648, just as Newton was sitting down to write the Principia, a Danish astronomer would offer an explanation as to why this could be true, one based on a fully heliocentric model of the solar system. Ole Rømer had studied at the University of Copenhagen and had taken a position at Uraniborg on Veen, the observatory that Tycho had built. He had undertaken the project of very carefully observing the timing of the eclipses of Jupiter in order to realize Galileo's hope that by using the timing of these eclipses, mariners could find their longitude, in essence taking on the same role at Veen that Flamsteed had in Greenwich. What he found was that while Galileo's predictions of the eclipse times worked really well when Jupiter was at opposition, i.e. 180 degrees away from the sun in the sky, or something that's about due south at midnight, they were off by an increasing amount the closer Jupiter got to conjunction, the time when the planet was as close to the sun in the sky as it would get. While making observations right at conjunction could be really difficult, Rømer could use trends in his data going into and coming out of conjunction to estimate a difference from Galileo's prediction, and he found that that difference was going to be about 16 minutes at the point of conjunction. Now this is where Rømer gets really, really clever, I think. This is just really amazing. Not only does he want to find out how the timing changes, but he wants to come up with an explanation for the timing changes. In the geocentric model, it's really hard to account for the varying difference, but in a heliocentric model, there is a way to do it. Up to that point, it had been assumed that the transmission of light occurred instantaneously, its speed basically being infinite. What Rømer realized was that if light actually took time to travel through space, like a bird or an arrow did, then there was a solution to the Galileo problem if one assumed a heliocentric model of the solar system. In the heliocentric model, when Jupiter is in opposition, it's on the same side of the sun as the Earth is. If you kind of draw a picture in your mind, or on a piece of paper if you have one handy, you can put the sun kind of towards the left, the Earth a small distance to the right of that, and then Jupiter about 5 times further away from the sun on the same side of the sun as the Earth, in a line with the sun and the Earth, so that if you imagine standing on the Earth, the sun is on your left and the Jupiter is on the opposite side to your right. In that case, Jupiter is about 4 times the Earth-Sun separation, or the Earth-Sun distance, a unit known as an astronomical unit, or AU, from the Earth. Okay, now let's talk about conjunction. If you think about Jupiter in conjunction, Jupiter would be on the other side of the sun from the Earth. Or, very close to being on the other side so you can still see it. And so, if the distance from the Earth to Jupiter was 4 AUs before, it would now be 6 AUs for the case of conjunction. And again, you might want to draw this out on a piece of paper so you can sort of see that. Romer recognized that if the light from Jupiter took time to travel across the distance of space to the Earth, there would be a time difference or delay as to when the eclipse was calculated to happen and when it was observed. This was the 16 minutes he was seeing in his data at conjunction. And he therefore estimated that the speed of light had to be about 8 minutes per astronomical unit. It's really a brilliant piece of work that has to assume a heliocentric solar system. For the Keplerians, it was another piece of confirmational evidence, while for the supporters of the modified Tychonic model, there's really no way to explain Romer's observations. Though it should be said that Romer's idea of a finite speed of light wasn't broadly accepted until a 1727 observation that we're going to discuss here very shortly. Interestingly here, it isn't Romer who does the actual calculations to come up with the speed of light. After publishing his data and his construction of how the calculation would go for any point in their various orbits, it was Christian Huygens who would take up the problem and come up with the actual numerical estimate of the speed of light based on the diameter of the Earth. Romer, for his part, would go on to make a number of other contributions, including designing better measurement instruments to measure the meridian crossings of the stars, the first street lights for Copenhagen, and convincing the Danish government to transition from the old Julian calendar to the newer and more accurate Gregorian one. In the year of Newton's death, 1727, as the 30-year-old Voltaire marveled at the spectacle of his funeral, the British astronomer James Bradley was making careful measurements of the positions of the stars and coming up with somewhat peculiar results. Like many others before him, Bradley was attempting to measure stellar parallax, that shift in the position of the stars that was thought had to happen if the Earth went around the sun. And like some of the others before him, he kept coming up with the result that while the stars did seem to shift, they did not do so in a way that was consistent with the predictions made for stellar parallax. Now, in the past, it had been assumed that these observations were due to error, that the shifts that were being reported were because the observers either had bad instruments or bad atmosphere to look through, or they were just careless or whatever. But Bradley had been able to reproduce the observations for the same couple of stars over and over again, and so he was able to show that the shifts were really above the level of instrument precision of his instrument. In other words, the shifts weren't because his instruments weren't accurate enough to make the measurements. So the question for him was, if the shifts are real, but they aren't due to stellar parallax, what was causing them? After working through and discarding a number of different explanations, the story goes that Bradley observed a weather vane and how the angle it was observed at was affected by both the wind and the observing position of the observer. This got him wondering how a moving Earth might affect or influence observations of starlight. And here again we see a leap of creativity when Bradley recognizes that the only way in which this idea would work would be if light had a finite speed and if the Earth was moving through space. And here's the key thing, you put those both together. While trying to recount Bradley's explanation through the medium of an audio podcast is very difficult, we can say that he did develop a theory to account for both of these, and thus he was able to explain what we now call the aberration of starlight that accounted for all of his data. This explanation required that the Earth move around the sun in a circular or nearly circular orbit once per year. He presented all of this in a paper to the Royal Society in 1729, and this is generally considered to be the first truly definitive evidence of the Earth's motion around the sun. In a sense, you could say this proved, at least at the time, that the Earth went around the sun, that the Earth did in fact move. It should be noted here that with the rise of the wave theory of light in the 19th century, after Young's famous double-slit experiment, Bradley's explanation of the aberration of starlight would be called into question, and the issue would remain unresolved until Einstein developed his special theory of relativity. The next significant proof of Newton's celestial mechanics, of course, came in 1758 with the return of the comet of 1682, just as Halley had predicted. This showed that all objects in the solar system obeyed those natural laws that Newton had set forth, and thus the comet's return was celebrated as confirming evidence of not only his picture of mechanics, but also as being supportive of the idea of heliocentrism. Halley's ideas would once again play a role when his sort of method for measuring the transit of Venus was tested in 1769, thus providing a fairly accurate measurement of the size of an astronomical unit, and again establishing through indirect observation the validity of a heliocentric model. Direct conformational evidence for the motion of the Earth would finally be provided in 1838 when Frederick Bessel was finally able to observe stellar parallax directly using telescopic means. In 1851, the French physicist Jean Foucault would demonstrate the Earth's rotation with the now famous pendulum that bears his name, which is found in museums of science and natural history the world over. By that time, though, at the beginning of the 19th century, the question was considered to be broadly settled amongst the scientific community. Heliocentrism was the correct model, though it would take these direct measurements to finally convince the Catholic Church and some institutions of higher education to lift the injunction on the teaching of heliocentrism. After the publication of the Principia, progress was spurred on by its ideas in fields beyond those of just astronomy and practical physics. As we've mentioned, the mathematical foundation of the work was dense and obscure, and so in the 18th and early 19th century, several continental figures began a research program to both formalize the ideas Newton presented and to generalize them in a more powerful and understandable mathematical form. Among the first to do this was Leonhard Euler, who developed a number of mathematical tools to analyze Newtonian systems. The next figure of note was Joseph Louis Lagrange, who built on the work of Jacques Bernoulli, Jean d'Alembert, and Euler to formulate a new way of expressing Newton's idea of momentum and Chatelet's kinetic energy in a way that emphasized the conservation of both these quantities. This led to a powerful new method of analyzing mechanical systems that's still taught in classrooms today. The pinnacle of this development would come in the work of Pierre-Simon Laplace, who, through the turmoil of the French Revolution and the rise of Napoleon, would publish a 5-volume work titled Mécanique Céleste, or Celestial Mechanics. In this effort, offered and considered the height of enlightened rationalism, he showed the solar system to be a stable system of gravitationally interacting objects moving according to well-understood physical laws. The genesis of that project had been the observed slowing of Jupiter in its orbit and the acceleration of Saturn in its path around the Sun. While there were those who questioned whether this indicated a failure of Newton's model, Laplace believed it was an issue of not taking into account all of the gravitational influences on both worlds, especially the gravitational influence between the two of them. In a mathematical tour de force, Laplace was able to derive from the work of Lagrange a new set of equations describing the motions of both Jupiter and Saturn that used nothing more than Newtonian gravity. These equations correctly predicted the motions of the planets as far back as the observations would be found within the error of those observations. And by the way, When I say as far back as it could be found, I do actually mean as far back as Ptolemy and even the Mesopotamians. There's a story regarding Laplace, whose work extends far beyond the brief mention we've made here, and to which I hope to return in a future episode, that is both wonderfully amusing and illustrative of the ideas of the Enlightenment with regards to religion. While it should be noted that, like all these things, there's a good bit of historical debate regarding the accuracy of the story, it should be noted that the discounters may actually have had greater reasons to want to distance Laplace from the comments that are made here. So, however you want to look at it, here we go. During the time when Napoleon held the title of the first consul of France, in around 1802, he had invited a number of notable thinkers to meet with him. Among them was William Herschel, the physicist and engineer Count Rumford, and the mathematician Jean-Antoine Chapal, and of course, Laplace was also there as well. Now, it was well known that Napoleon liked to either embarrass intellectuals or at least make them uncomfortable by asking sort of very awkward questions. And so, after talking to Huygens, he then turned the conversation to Laplace. And he is said to have said something to the effect of, "Well, Monsieur Laplace, I have looked over your great book, and some of my people have read it in some depth. It seems like quite a profound work. What I found interesting is that while Newton, in the Principia, invoked the intervention of God to keep the solar system running smoothly, you make no mention of the Creator." You know, that's really an awkward question in a social gathering, don't you think? And of course, Newton asked it to get the young man to squirm a bit. Instead, though, Laplace, always a bit touchy about matters of religious and philosophical import, drew himself up, looked at the first consul, and somewhat dismissively replied, "I have no need of that hypothesis." Now, as I said, there's some question as to whether such an exchange actually took place, especially with such an exquisite riposte at the end. But in an age where verbal sparring could be a matter of life and death, and the ability to stand one's ground rhetorically was a requirement in the salons of Paris, it's certainly not out of the realm of possibility that Laplace shut the little corporal's comments down in no uncertain terms. What's also telling here is that Laplace can make such a statement and not really suffer for it. 100 years earlier, he would have been censured and perhaps imprisoned for such impiety. But with the religious skepticism of Voltaire now fully accepted in late revolutionary France, Laplace's either deism or atheism was no longer a liability to his standing in the intellectual communities of Europe. Instead, what we find in Laplace's writing is the cold, hard presentation of determinism, the idea that free will is an illusion and that all things are determined by matter moving through a void according to natural laws. In his words, quote, "We may regard the present state of the universe as the effect of its past and the cause of its future. The intellect, at which a certain moment would know all the forces that set nature in motion, and all positions of all items of which nature is composed, if this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of all the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes." End quote. What I find fascinating is that while many may reject Laplace's deterministic worldview today, we live in a world where his ethos, coded into lines of computer instructions, is used to predict the motions of the planets and stars of the heavens, the ebb and flow of air masses and jet streams here on the Earth, the spread of viruses across populations, and the folding of proteins inside of cells. We live in a world where we take for granted the unerring action of the laws of nature, first put forth by Newton and developed by the great mathematical minds of the following century. One thing we've skipped over is the work of an army deserter, a musical teacher turned amateur astronomer who saw for the first time what many others had seen but missed. In our next episode, we'll start with the work of the Herschels in Bath in 1781 and go hunting for planets. Along the way, we'll examine some of the greatest failures and some of the greatest triumphs science has to offer. As we wrap up, let me make a couple of quick announcements. First, faithful listener Andrew Mintz has informed me that the position of Chief Astronomer to the Crown of Britain is not the Astronomer Royal as I've been saying it, but rather just Astronomer Royal. I learned it differently growing up, but I can see how such a Francophile pronunciation of the title would be a bit grating. Thanks, Andrew, for keeping me on track there. Also, I'd like to acknowledge the Renaissance Mathematicus blog by Dr. Tony Christie as the source for some of my information on the adoption of Newton's ideas, specifically the work of the two great women physicists who spread his ideas through France and Italy. As we finish up here, I'd like to ask you to remember to stop by our Facebook page to weigh in on the graphic designs that we're thinking about moving forward. We'd like to sort of wrap that up here in the next week or so we can continue on with new designs and new efforts built on what we've already got. Also, let me once again say thanks to each of you and to all of you who take the time to listen to the show. Every once in a while, when I'm not scrambling to find sources or do some reading or write an episode or some other thing like, my real 40-hour-a-week or more job, I get a chance to realize that there are about 1,000 or so of you who make some space in your week to listen to my ramblings about science and its history and its philosophy. And when that happens, when I sort of pause and I reflect on that, I have to say that I'm more than just a little humbled. While it's a little strange to be sitting here in my back room at the house speaking into a Blue Yeti microphone, in other words, sort of talking to myself, I like to imagine you all taking in my words and thoughts and mulling them over in your heads, and hopefully feeling just a bit of the wonder and excitement I do when I consider the work and ideas of all of these fellow human beings of ours who have had a part in creating the picture of the universe that we have inherited. It really is a wonderful part of our shared heritage, and I'm honored to be able to journey with you all through it. So again, thanks for making me and this podcast a part of your life. Until next time, full sails on your journey.